We have a CSS file. So, okay, Jupyter Lab. Press Jupyter Lab. Do you see that? You know how to run the server, right? I've already prepared this for you. So just input Jupyter Lab. Now go back to remember your IP address. Okay. Here, do not press enter yet. HTTPS. This use HTTPS. No port number. The port number is, I said port number default is 443, which is encrypted port number. You should be on this page. And then keep continue. Here, password, CSS. Enter. I know it's a little frustrated, but it's part of research. Week 5, go to week 5, CSS exercise, week 5. Open this file. Open this file. First, just to run this block, the first block. I will elaborate each line of this. For now, let's just run through them and let the computer download a lot of stuff. The tokenizer is easy to download. And the next thing we need to download is a very large file of quick hand is here. So what to vec example. Click this. What to vec example. Click here. You click here, you will see there is a menu here. Then click what to vec example. Google News. What do we need to download? What do we need to download here is a Google News language model. It's about 2 GB, 1.6 GB. So it will start to download. Click here. Too small. This is too small. Okay. Okay, download this thing. This thing is big. Other than that, we also have the Glove, GLOVE, navigate to Glove. This is GLOVE. This file, we need to download as well. Just exit this command. Just exit this block. I know the previous block is running. Let it run. Just let this run. It will stay here. It will be kind of queued here. There will be executing sequence. Okay, we'll let it here. Now, well, okay, we get the housework done. Just cleaning the house, yeah. While the machine is downloading the file, it's pretty very slow because you see this spitting out a lot of information. So it is crashing your browser. Yeah. Your browser is crashing. It's freezing. It's freezing. Yeah. Don't touch it. Don't try to. Just let it go. It's slow. It's just slow because your browser is a kind of commercial browser. But what you are using now is a supercomputer. It's a kind of large machine. It can easily crush your small browser very easily. Okay, now I have it, and I will go through this again. Now let's switch back to human language. Switch back to the course, the lecture. So, watch it. Okay, so for this week, we have we will review. First, let's review a few stuff. We have Professor Paul van Hippel join us today. So Professor Paul van Hippel is our associate dean here for academic research, and also he has a lot of research which will be using text analysis. So if you're doing well, probably he can be a future boss at this class. He's hiring. No. And also we probably don't know he has 2 PhDs, one in music, one in sociology. And his early kind of publication are all in music, the rhythm, something, the pace of the music, something like that, right? Yeah, very interesting, very interesting. And probably he is pursuing his third PhD in data science. Okay. That's amazing because it's very aspirational because after you graduate from school, your learning cost is very high. So sometimes you need to be very determined to get another PhD. I don't have a plan for now. Okay, so for the student-led seminar on research design, data management, which will be next week. So for this group, you should be preparing right now from this week. You should be preparing. I already provide you some readings. These are recommended readings, which will give you. It's more like a kind of enlightening readings. From these readings, you will get a sense about what it is, what are the frameworks, right? You can start your own. I have my own idea, but you probably have your own idea too, right? Construct your framework, try to deliver a lecture, and let a student know what it is about. Again, framework is very important. For the details, go to the assignment. The assignment, I have highlighted a few things that is very important for us to know. And also empirical readings, you need to decide at least the 2 empirical readings from the database I provided, and also another 2 empirical readings you identify. That is not on my list. For the entire kind of lecture part, you should be able to expect. You should expect to finish that before 10:30, the kind of first half of the class. Then for the rest of the half of the class, starting, I will make some comments. I will give you some feedback. I will give you more ideas from my own, and also we will spend those time on your final project, because this final project is really something you will use your skills, not as assignment. That's the kind of expectation about this. Okay, let's have a short break. Setting up computing environment, logging instance, start a Jupyter notebook, download the working directory of this week, SSS, Google News, and Blue. We're already here. We already finished this page. Okay, so this week we have several pieces of reading. 2 of them are methodological. One of them is very technical. So this reading we're not reading. We haven't read this, but it's a very well-known paper published in 2013. Talk about text analysis, text as data in political science. But this is widely read by a lot of social scientists and many other disciplines. It gives you a sense about what a kind of data analysis is. How can we give them a category? So first, you acquire documents. You can from existing documents, electronic resources, or undigitalized text. For example, PDF, you take a picture, then you need to do OCR, right? Which is not hard. Now a lot of packages. Right now I'm using a OCR package. I found it amazingly good, You do some pre-process. We will do that. We will practice that later using the notebook I provided to you. And the research objective, you should identify a research objective. Well, so this diagram can be used as a reference, but do not use it as kind of gold standard, because sometimes it mix the results and the process is mixed. Remember that it is very flexible. Depending on your research project, it's very flexible. Sometimes you have your research objective, right? Then you define how you pre-process your data. Because according to your data, some of the text may be important, some of the text may be not important. So you want to the pre-process, sometimes you need to consider what kind of research you are going to do. Research objective. There are 2 types of research objective. One is classification, another one is ideological scaling. If we start from statistical perspective, classification, you transfer all these text into categorical data, like left and right, liberal and conservative, something like that. It's must be categorical in your regression analysis. Ideological scaling is something more continuous. When I say more continuous, it doesn't mean that they must be categorical. They must be continuous variable. They can be discrete. They can like numbers from 1 to 5. It's just a kind of it have a kind of a finer interval than this categorical. Categorical just a screen, it's just categories, right? but there are some relationships here in the ideological scaling here. For this classification, you can use known categories or unknown categories. It actually corresponds to the supervised or unsupervised. Everything below here, actually, they share a lot of similarities. They do not differ too much. Like known categories, if you use a machine learning algorithm, it will be supervised machine learning algorithm, right? If it is unknown categories like topic modeling, it will be unsupervised machine learning algorithm, right? And also supervised and supervised can be done in another way, which is being dictionary approach. Very simple. You have a dictionary of words, and if this article hit those words in your dictionary, you give 1 score of that dictionary, like a dictionary of happiness. You have a lot of words about happiness. We will see an example. So from a computational perspective, this is the research design perspective, right? Because in research design, I need to know whether I have a known category. If you have a known category, you have a framework, right? Like a theory. Some of you are doing your research. You have a framework already. So according to the framework, you probably will have a known categories because you have a theory already. But if you don't have a theory, you just are doing unknown categories, you can do topic modeling, right? Sometimes they can merge too. For example, I do have a theory, but I still want to let the data tell. And then I ask the data to do the unknown categories and do a topic modeling. I will see some topics. And then I will see whether these topics can be put in these categories, in this established framework. If it is perfectly fit, okay, the theory is good. If it is not perfectly fit, then probably you are advancing the theory further, right? That kind of relationship. Again, remember, flexibility is a key here. There is no right or wrong to do. There is no single way to do a text analysis project. Supervised, unsupervised, that's the same. And then they have a lot of kind of things here. I will elaborate each of them, but you have a sense, right? Dictionary or machine learning approach. Dictionary is very kind of unflexible. Like you have a dictionary of words, but machine learning is more flexible. You are training. You don't have to invent a list of categories, something like that, right? So machine learning is more flexible. We will touch on machine learning in the coming weeks as well. We have a diagram and teach you how to do machine learning. Dictionary of methods, I talked about that. I talked about that. Supervised methods, machine learning is one. Fully automated clustering, computer-assisted clustering. So fully automated clustering, like you do K nearest neighbor, something like that, without any domain knowledge. This kind of fully automated clustering. But the example I just provide you, for example, I do have a theory behind, so I do know there are probably a few categories, but I still want to see how I can put this kind of a topic modeling results into those buckets. I already know this kind of computer-assisted clustering, right? So you are doing both. You have your domain knowledge, and you also have the clustering results. Everything underneath here, you don't have to go through them. A lot of them are very outdated right now. 4 principles of automated text analysis. First, all quantitative models of language are wrong, but some are useful. So validation is key. Quantitative methods augment humans, not replace them. They would help you to do research and not replacing you to do research. Sometimes if you think the question, even human cannot do the topic modeling or cannot do the scaling or analyze the text, and you rely on computer to do this, almost not possible. When I say not possible, I mean that computational, that cognitively, not computationally, right? 10,000, can you do 10,000 documents? Computationally, it's hard, but cognitively, probably it's easy, right? If you just categorize these documents to negative or positive, right? Cognitively, it's easy, but computationally, it's hard. It's not impossible. So here, when we say computations or algorithm can replace human computationally, but not cognitively. There is no globally best method for automated text analysis. So try all kinds of methods. Do a lot of experiments. That's very important. That's what I do in my research as well. Sometimes I don't know which one is better. And you need to have because you have domain knowledge, right? Sometimes you need to find a way to evaluate the results. For computer science and social science, we are different. Computer science only care about, say, precision recall, or they will invent other metrics like PMI, which stands for an algorithm that can evaluate how much information is extracted from the text, which is purely computational. But that's not our approach. Computational and meaningful doesn't mean it is social. So in social science research, most of the time you need to rely on your domain knowledge to devise some algorithms or some criteria to evaluate the validity of your instruments. Validate. The gold standard is still human manual validation. There are different ways to do the validation. You can do it by yourself, and there are a few tools online. You can crowdsource this work out to the online platform like Amazon MTurk, and I think Qualtrics also have those kind of services, sampling services, something like that. Yeah, JP.
Can you describe what that means, validate in this context?
Yeah. For example, your job is kind of to categorize the text as liberal and conservative, right? You develop an algorithm. Then what you need to do is, okay, you manually classify 1,000 text. That's what your manual result, right? And then you ask a computer to classify the 1,000 and see the consistency between the computer results and your manual results. That's kind of validation. This is kind of validation. Yeah, this is just one way to do the validation. There are other ways, but this is most common ways to do the validation. Make sense?
So you're talking here about supervised classification.
Supervised. Yeah, unsupervised. We can do unsupervised as well. It's just depending on the context. Again, there's no fix. As long as the results. I mean, I think the general idea behind this is, okay, we are very critical about the machine-generated results. No matter it is unsupervised or the supervised results, I want to validate it. And this is very important. This is very important for social science as well, right? Because we are always criticized to say, you just garbage in, garbage out, right? So that's always been criticized by using the big data kind of stuff. So you need to validate the result, no matter what kind of approach, as long as it is computer generated. So think about it, even sometimes your GA, your research assistant help you do some results. You want to validate as well, right? Let alone a kind of a computer algorithm, right? So just the whole rationale behind this, be critical about the results produced. Future readings. So this reading published a year ago. I think they published actually 2 years ago, and then officially published a year ago. What embeddings, what works, what doesn't, and how to tell the difference for applied research. So this article is very good. It compares different language models and try to navigate which model or which method is actually more useful, quote unquote. Useful can be defined in different ways to social scientists. And they run extensive experimentation on various kinds of language models. I suggest you read this. Then you will know, okay, why you should be cautious about why we need to validate, how we validate, and what kind of a result for validation. So those authors are primarily political scientists. They have some computer science background. So their validation is very different from what you read in computer science journals. They're very different flavor. Natural language processing research. A foundational tool is regular expression. This regular expression is, if you want to do anything about text, learn regular expression in the first place. Regular expression is the key you want to learn. But right now you have ChatGPT, right? Somehow I found myself became a little lazy. Before ChatGPT, I write my own kind of a regular expression. You can test regular expression online. There are some online regular expression tester. Yeah, I usually use this one. I have a cheat sheet. I found this cheat sheet very useful because you cannot memorize everything, right? So you can test the regular expression here. But right now, what I do, I just open ChatGPT. I give them a sample text, and it tells ChatGPT that I want to extract this text from this text, and ChatGPT will spit out, tell me, okay, what kind of regular expression I should use. I tried that twice, a couple of times, but I think only half of the times it really produced something I want. For the other half of the time, like a little complicated thing, I need to revise it extensively, right? Then ChatGPT cannot replace you. If you can, for example, if you take this kind of regular expression test, you can only get a say 80 score on 80. It cannot assist you and get you kind of 90, something like that, right? So you should learn this by yourself as well and get it understood, at least in a kind of intermediary level. There are courses on R and Python. You can follow that course. You can use that course. And there must be a lot of other kind of online tutorials. But there's regular expression is so fundamental in NLP. Common approach, words are strings. So if you read the Jurafsky's article, a book chapter, it talks about usually we treat text as two types of things. One is we treat words as strings. 1 is 1, 2 is 2, right? And I love computational social science. It's just a text. They are forms. They are kind of text. They are strings. Another is treat them as carrying meanings. Treat them as carrying meanings. So a quick example about treating words as strings are these LIWC, which is commonly used in psychology, and also produced by, I think invented by the professor in our psychology department. So I think he invented this kind of LIWC in 1990s, and in early 2000 they commercialized this. So it is widely used in industry and in research as well. What they do is they have a dictionary. You click dictionary here. Okay, you have to. Yeah, they were not that. They were more transparent than this. But that's okay. We have this screenshot here. So this is a category: positive emotion. For example, love, nice, sweet. There are 406 words in this positive emotion. If you have an article, it's literally just a count how many words in the positive category in your text, and then we'll give a score. We'll normalize it according to your length of the text, and then give a score to your text. It's just a easy dictionary approach, right? So you see, the dictionary approach are actually treating words as the strings. Match them. I don't care their meaning while matching, right? I don't care. And then there another approach is we treat words carrying meanings. Dictionary approach, LIWC, I introduced that. And also minimum editing distance. Yeah, I'm not finishing on the word strings, words are strings yet. So minimum edited distance is, okay, how to change this word, how to change the word from this one, to intention to execution. You calculate how to edit them. Like if I is delete, I delete I, N, I will substitute N with E. I will substitute T with X. I will insert C here. Then I will substitute N with U. Then I will get the execution. And each of them will have a score. So that means this kind of cost called edit distance. So this is one way to measure the similarity between text, but still treat them as strings. But depending on what's your research question? don't think that kind of these methods are obsolete. No, they are not. For example, in one of my research, I need to match the. So I'm studying how English articles are cited by Chinese scholars. So I need to match the English articles and the references, the citations in Chinese articles, right? I need to match them. Otherwise, I don't know whether this article is an article, right? So semantic, I do not need to treat them as meanings. I need to treat them as strings, right? Because I want to match exactly the same article. Then I need to use this method to help me have a calculation. Usually, I will have a calculation. I will draw a distribution of the score. For example, for each of the title, I will have a number. I will have edit distance. I will draw a distribution. I will found, okay, probably here is about to say 80%. 80%. You will naturally found there is a cutoff point here, like 80%. Then I will use 80% as a cutoff point, and then for this part, I will let it go. I will think, okay, they are almost the same, right? But for the rest, I will double check. I will use other methods to treat them because they are less likely to be the same article. That makes sense? Yeah. Any questions on this? And also there are bag of words approach. Like this one, how you construct the count vector. You need to have a vocabulary, very much like a dictionary. For these 3 sentences, the unique words I have, we focus on education, healthcare, about. For this sentence, we focus on education. This is 1, 1, 1, 1. No health, 0. Care, 0. About, 0. Then you will see I have a vector. This is my vector, right? Then it became a vector. I vectorized this sentence using this vocabulary. Because I'm using the same vocabulary, I can compare and I can calculate these different documents. For here, not here, but here. So I have a vector of 1, 2, 3, 4, 5, 6, 7. I have a 7-dimension vector for this sentence, and I also have a 7-dimension vector for this sentence as well, and also almost this sentence. I can calculate the similarity. How I calculate similarity? You can imagine if they have if they share the same, if they are exactly the same topic, or the same contain the same text, usually you think that the vector is the same. Vector is the same, right? If they share more words, the vector will be more similar. When I say similar, means their cosine similarity, or the inner dot vector, inner product or dot product of the 2 vectors. We will see one example later on the notebook. In the notebook. Words carry meanings. It will be something like this. So similar words with similar meanings, they will be putting together here like this. By now that these are all kind of functional words. These are very good, incredibly fantastic, terrible, terrific, not terrible. Here are all words with kind of negative meanings. So treating them as meanings. How we get this? We will get there. But just to give you a quick sense, when we treat the words as meanings, you will see the words with similar meaning that will be very close to each other in the same, in this we call semantic space, the same semantic space. How we get this semantic space? We'll get there. During another example is during GRE test. Those GRE tests probably will be waived. During GRE test, what's the most important strategy when you see a stranger word, like a reading test? Skip it? Okay.
Everything tight on time, right?
Yeah.
Pragmatic.
Look at the other words.
Yes, yes. That's how this.
It feels like I'm out.
Yeah, you know, I didn't do too well.
I applied when they were like, we don't do it, we're not doing it.
Okay.
Yeah.
This is another way to try to understand how to treat words carrying meanings, right? So the word actually the word's meaning can be expressed by its surrounding words, right? Surrounding words in a context. I like this quote from the Jurati. They translate the sentence from a kind of an ancient Chinese philosopher. 言者所在意，得意而忘形, which means words are for meaning. Once you get the meaning, you can forget the words. That's very philosophical, right? So now we're not talking about the strings, we're talking about the meaning. Another thing I get from this is about programming. So why I was the first time I learned programming was I was in primary school. I was 8 years old or 9 years old. So at that moment, I didn't learn English yet. But I have to use this kind of English language. If I don't know if put together means if, right? I have to recite them. So to me, those just a string, they just carry meanings. What really important is the logic behind, right? So that's kind of you don't need to take care about the form of this thing. What you need to really care about is the meaning behind, about meaning. This is another graph example from my current working paper. What this math tells you is, do you see all these blue small dots? They are one English article. And for this kind of a red dot, for this kind of a blue dot here, without Chinese text, these blue dots are indicating the English research topic, For these red topics, you see there are Chinese characters behind, means they are Chinese research topic. And through this meaning, if we forget about the form of the language, just think about the meaning of language, we can map them on the same map. And we see actually cross language, the article, the text can be mapped very close to each other. Like this topic is about economists, Smith, Marx, and you see the Marx is here, the Chinese Marx is here, their research is here. They're very close to each other. And also here, like this peasants' political participation, and they are very close to democracy, authoritarian election, something like that, right? Here. And also here, housing, farming, and poverty is very close to irrigation, farming as well in Chinese, which means in Chinese context, it's probably the irrigation is a public resource problem in Chinese context. But in English, the household, farming, and poverty probably is a more emergent problem in English word.
So this is, I guess, a personal question for this research. Are you hoping to find like any types of similarities or differences with regards to, I see like Marx and a lot of political stuff?
Yeah.
As in the political party next to democracy or the election.
Yeah.
Like that's
Yeah.
the perspective of where US perceiving.
Yeah. It's next to study. Yeah. And that's a very good point. So you can expect I have another graph show you how these Chinese articles are citing English reference. For example, in Chinese article, there's a term called political civilization. What is political civilization? We know what is civilization, but political civilization we don't know. These articles cite a lot of articles about democracy in English. Can you imagine why these kind of authoritarian literature are talking about also? They are also talking about democracy. They are also citing Tocqueville, Max Weber, authors like that, right? But the context is very different. And they try, the scholars try to reframe them in a different political context. Again, what I'm saying here, no value judgment. It's very important to stay value neutral. I'm not saying, okay, those scholars are just doing something, just try to legitimize something. They are doing serious research, quote unquote. They are doing serious research as well, right? They are still doing serious research. So it's very important to see how these concepts invented or theories invented in one language are transformed in another language. and reframing in other language. And now you have to get over the language barrier. When I say language barrier, is a form of language, but not the meaning of language. So that's kind of a multilingual topic modeling is very, very important in this study. So get words embeddings, what to back. Okay, I hope you can help me read out because this is very, very classical, very classical. And I found that no other text can get a better kind of expression about what is back to back, what to back. Let's start with JP, and can you help me read out this paragraph?
Yeah, sure. The intuition of word to vec that instead of counting how often each word W occurs near, say, apricot, will instead train a classifier on a binary prediction task. Is word W likely to show up near apricot? We don't actually care about this prediction task. Instead, we'll take the learned classifier weights as the word embeddings.
Yeah, there are some terms here. I probably need to give you a little background about this. Is when you do machine learning algorithm, you know what is weights, right? Especially with neural network, there are different nodes there. So like you have a node here, hidden node, and the different node that will have weights. When you connect them, it's just to let the computer know, okay, if I get true or false, if I get true for this node, I go this node. If I get true and this node false, I get this node, I go this node. Or I have a weight, like this is 0.3 or 0.7, something like that, right? What we really care is the weight of the training of the trend classifier instead of what the value is, right? These are the weights. These are the weights we're talking about. And how to predict is like this one. The algorithm will be something like this. I will just try to predict whether amazing is close to very good. Is close to very good. It's kind of a binary prediction task, right? Yes or false. It's kind of a genius. Let's see why it is genius. Next paragraph. Leonard, can you help me read the second paragraph?
The revolutionary intuition here is that we just use running text as implicitly supervised training data for such a classifier. A word C that occurs near the target word apricot acts as gold correct answer to the question, is word C likely to show up near apricot? This method, often called self-supervision, avoids the need for any sort of hand-labeled supervision signal. The idea was proposed in the task of neural language modeling when Bengio et al. And those guys showed that a neural language model, a neural network that would predict the next word from prior words, could just use the next word in running text as a supervision signal and could be used to learn an embedding representation for each word as part of doing this prediction.
Isn't that amazing, right? How would this clever person think about this? So clever. Every day when you write something, it's kind of a training text for algorithm, the self-supervision. Next paragraph. Rachel.
We'll see how to do neural networks in the next chapter, but word2vec is a much simpler model than the neural network language model in two ways. First, word2vec simplified the task, making it binary classification instead of word detection. Second, word2vec simplifies architecture, creating a logistic regression classifier instead of a multi-layer neural network with hidden layers and more sophisticated training algorithms. The intuition of skip-ram is 1, treat the target word and neighboring context word as positive examples. 2, randomly sample other words in the lexicon to get negative samples. 3, use logistic regression to train a classifier to distinguish those two cases. 4, use the learned weights as the embeddings.
You probably are not crystal clear about each step, but you get a sense. That's good enough. That's good enough. Here is another example. So when we say training window, if you do the training by yourself, you will say there is a window specification parameter. what that window mean is like a source text, we have the quick brown fox jumps over the lazy dog. So if we have a window of 3 words, is this kind of 3 words. What we need to predict is whether the is our target word. And then we want to know whether quick is neighboring with the on the brown is neighboring with the, right? So we have the training sample here. So here we move from here to here. Now we have kind of a 4 window. This is kind of a 4 words window. So quick is our target word. And then we see the brown fox. They are close to each other. We have a training sample here. Think about that. If we go through a text like this, 1,000, 10,000, 1,000,000, we will be able to find some patterns like this. Right? And then we use this kind of a training, even without doing machine learning algorithm, we should be able to find this training sample. Sometimes we call this n-gram. This is again called bigram. Is that 2 words together? Right? You will see a lot of patterns will emerge even through these training samples. And if we use this training sample to train an algorithm, a classifier, you will see some of the kind of words that will appear together very often. They will have higher weights, right? If they rarely appear together, it will have lower weights. The weights will be lower in your machine learning algorithm. Make sense? Yeah. How we can use them? Okay, once we got their weight, we got a vector. Now we know once we vectorize them, we can express them in this kind of space, right? This space. And we can also express this in this kind, even cross language, we can do this in this space. We will do a quick bilingual example later in the notebook as well. We can put them in this space. And there's another example here with studying implicit linguistic stereotype and biases. How this kind of a research method can help us as social research, social science research, like linguistic stereotype and biases. King and queen, they have closer relationship. They have their distance should be very close to the distance between man and woman, right? So then you can calculate queen minus king equals to women minus men. Then you can calculate them like you calculate 1 plus 2, like you calculate numbers. This can help us to study the linguistic biases. Like the most famous article about is man to programmer is like women to housewife, right? Or man to doctor is very much like women to nurse. That's linguistic bias within. It's true everywhere. I will show you a quick example later. So here we can also visualize we can have several dimensions: race survey and also class survey, and this race projection, and here is the kind of class projection. So these produce all those words about the music on these different dimensions. Like this opera is on this side, rich and white, like opera. Okay. And here we have some kind of poor white. We'll have blue, grass, punk. It's harsh. It's harsh. But let's say, okay, this is academic research, and they are real. They are real in our everyday language. They are real in our everyday language. This paper is very good as well. I have linked to the article on the web page.
So may I ask a question?
Sure.
This is all about using proximity of words,
Proximity
approximate
of words.
meaning.
Yes.
But you could also approximate some aspects of grammar, right? So if a word appears near the word the, then it's probably a noun.
Yes.
Okay.
There are another technique called part of speech tagging.
Uh-huh.
So you want to know what's the kind of attribute of this word, and the word appear in like the word after the. Sometimes it is noun, sometimes it can be adjectives, right? So it varies. There is another kind of NLP task which can use a machine learning algorithm to tell you the possibility, to tell you what's a kind of a profile, what's the kind of the part of speech tagging of this. It can tells you this word is a noun, this word is a adjective, something like that. We will see a quick example too. And this is this is fundamental to NER, name entity recognition. We will do a quick example if we have time, okay? But we have everything there, so it should be quick. So here I'll show you another example. Studying implicit linguistic stereotype of biases, you see the male gender bias. For this paper, these authors develop a kind of index. So these numbers are showing you the relationship between gender and some other words. Actually, sometimes we call it attribute word. Family, yeah, this is family. This is for male. This is male. These are all association with male. So these are years. So time, you see the family, the association between male and family. Initially, it is negative in about 19th century, at the beginning of 19th century. Gradually, it is increasing. It is increasing, which means that family, the association between family and male are higher than in words. And which is good sign, right? It is good sign. But it's still negative. You see, it's still negative. However, you see this one, the green line is our career. So career, the relationship between male and career is much higher, and is positive. But through time, it is decreasing. So here, this shows you the family gender association over time. This is average pairwise conditional. Okay, this is a female family gender association. This shows you the female family association. This shows you the male family association. So female family association is here, well above male family association. Here. Right. It discloses, it's very descriptive. I know it's descriptive. But it tells us the biases we have. And you can imagine that we can use this as an independent variable or dependent variable to see how we can change them or how these kind of biases can influence our behavior, right? So how is useful? This article can be published because they are first in the field. But if you write something right now, it is too descriptive. People say, okay, we already know about this. So why you're telling me something I already know, right? So what we can do? People will ask you, what we can do about this? Then what you need to do is kind of another step. Okay, now let's start coding lecture. Okay, now let's have a short break. Let's come back 15 and then we start to code. Yeah, no problem. We have
Yeah, thanks for. So is that the only one?
That's your way.
Yeah, hey, you
Also, I can
there.
chmod.
yeah, okay, so you haven't back.
have to come.
Yeah,
Sometimes just take a long time. So be confident there is something going on there. One way you can check that is use htop. You see, okay, one CPU is running. We have for this CPU, for this machine, we have 96 cores, which means probably. So my laptop is 8 cores. It is 12 times powerful than my laptop. If you use them in a parallel fashion, if you just use them in a serial fashion, if you don't parallel, it's actually not good than my computer, because each core on my computer is better than each core on this machine. Make sense? So the real power of this machine is to do parallel instead of do serial. Okay, you see there is no bar there, means nothing is running. I think my result, I should look at that. I got my result here. So this is a way you can check. Okay, the machine is running. There's something going on there.
You just typed in htop.
Htop, yeah. I already pre-installed, so you should be able to htop this one. Is htop. I usually put them side by side, so I know. Okay. There are a few key information here, like this memory. We have about 108 gigabytes of memory, which is large, but sometimes it is not enough. So You want to monitor this memory. It is not memory out of memory. Usually you will get often I will get an out of memory problem.
You mentioned that if I'm unable to navigate the window of the server or like my actual server, then it's just everything's working. Because I'm trying to type it.
Yeah, probably is, yeah, just a wait a little bit, probably just execute the command right now.
Yeah.
Yeah.
It's still running.
It's still running,
And even like,
slow down.
Yeah, you use-
literally the time that you just walked over here. it
Yeah.
started. It's
So another way you can check to see if your kernel is running, see the kernel is idle. It is not using, right? The kernel is not busy right now. But sometimes there's a problem. So this interface can be disconnected from the kernel. So you actually really don't know what is going on there. What you can see is here. I usually use this interface instead of use that interface to see what is really going on there. Okay, I will show this interface later, but right now let's focus on the script. So in this notebook script, we'll be touching on a few things. First, we'll try to do word-to-vec, doc-to-vec, semantic similarity, and also we will try to do some pre-processing. First, we do pre-processing here. I will clarify each of these package and their usage. OS is there are a lot of system command line here. So I use OS to execute a lot of, most of the time I use OS to for some kind of system related operations, like list how many files are there in the folder and execute a command, something like that. Stanza is a package used for NLP, many NLP tasks. But primarily I use it for pre-processing. You can also do sentiment analysis. You can also do the NER as well. We will use a few examples. CLD3 is a package for language detecting. So it tells you the paragraph is wrote in English, Chinese, French, or any other language. So it language detection. Login is a package I use to log the progress because you want to monitor the progress of all your program. Random, just a package. I want to generate a random sample. I use random. NLTK, very famous language NLP package, primarily for some basic usage like pre-processing. Touch is a more advanced language model package. They can deal with a lot of neural network advanced algorithms. Pandas data frame, don't have to talk too much. Multiprocessing means multiprocessing, just a multiprocessing. Tools from partition is just some tools. Partition is used to partition the list I have. For example, I have a list of 1,000 items. I need to divide the 1,000 items into many groups, and each group only have 5 items, something like that, right? So it's partition. TensorFlow hub. TensorFlow is machine learning foundational framework or infrastructure developed by Google. And TensorFlow hub have a lot of language models where we can directly download or input instead of we invent by ourselves. In this example, we will be using the multilingual language model. TensorFlow text is here to fix a bug. Why it is here, I don't know, but it's here. And I found a solution. Here's a solution. And here's a link to the solution. If you are interested, just go there and read. NumPy is a scientific calculation. It provides a lot of math functions, like find the inner product of 2 vectors, acquire the mean of a list of numbers, something like that. NLTK download, I'm downloading punctuation, and I'm downloading all the stop words. And this touch.coda is available. Show me whether the GPU is available on this machine. It is not available on this machine, so it's showing you false. You see downloading. Yeah, you execute that. Pre-processing. Oh, another. Since we don't have time, my original plan is type them line by line, but we don't have time. For you, I strongly suggest you type them line by line when you practice. There is a very famous book, Learning Python, called Learning Python in the Hard Way. And that's the best way, actually. So that book tells you how to learn Python in the best way, or the hardest way is to type everything, do not copy paste. Unless it is something like this, some kind of URL or kind of a long name string, something like that, you can copy and paste. For the rest, just type them, It is amazingly important. So pre-processing, let's open one of the texts. This is a text I built there. So what I want to do is I want to do a pre-processing with NLTK, lowercase and tokenized. I want to change all the, let's see what we have here.
Sorry, is that text? Okay, it's a text document.
Doc. Yeah. You see here, we have all the documents here, right? You see here?
Could you also be a Word document?
No. It can be Word document, but you need a specific package to read.
Oh, okay.
Yeah.
So typically your files, you should try to get in the text document.
Yeah. So TXT is plain text. In machine world, TXT is far better than Word document. The Word document is not very popular. Most of the time in my research, if you do Word document, I even need to extract the text from the Word document and save it as a TXT file.
Got it. And can you open multiple at a time?
Yeah, you can, sure. Parallel.
Okay.
It's just for this purpose, I just show you how to do it in serial fashion. But you can.
Forgive me, what is the source here? What's in the document?
This document is a policy document wrote by this organization. Well, I don't know what's the name of this organization, but it seems like a kind of an international NGO or think tank.
Mm-hmm.
Just import a random kind of a document here for you policy practice. Okay. So here we have the docs here. These are the content of the docs. They have a lot of these docs. So we need to do a little bit with the text, right? You see, there are a lot of information not used, like Z and something like that.
Yeah, if you just run doc there.
Oh, yeah.
Text, okay. Or you could say doc head or something.
Yeah, you need to put doc here. So here I set this to this doc, but now I need to show the content of the doc and just type this like this. This doc. First, we want to change all the we want to normalize it. We want to make everything lowercase. But sometimes it's not effective because it's not recommended. Because like some places, they are case sensitive. Some of the words are case sensitive. It is not dealing with that. But now let's see. This is a very native example, very basic example. So from NLTK, import word tokenizer. Word tokenizer. I use this word tokenizer. Doc lower is this function will change every string text to lowercase. You see, all the text are in lowercase right now. Right. And now I put this text into this Word document, Word tokenizer function. I set this result to a doc tokens. What I get is how the first 10 tokens, how does earnings inequality affect Social Security finance? Question mark. What's next? I need to remove some stop words. So from NLTK covers, import stop words. There are already a list of stop words I can use. I don't need to invent myself. So, and then I set the stop words, I specified stop words as English. I set them to stop words. Let's see, what are those stop words are there? I, me, myself, we, our, ours, ourselves, etc. Won't, shouldn't, wasn't, a lot of words here, right? What you need to do is we just remove them from the tokens. Here is a called list comprehension. It's a very dense way to write the language. Here is word for word in doc tokens, if word not in stop words. Make sense? Very straightforward, right? So I need to list all the doc tokens if they are not in, but only if they are not in the stop words, right?
So I'm sorry, it's called a stop word because
They do not carry too much meanings, and they are functional words in the text, something like that. Yeah, it's just how people call it in linguistics, kind of called stop words. All NLP folks call it stop words. But there are more caveat way to do that. Like you know, LIWC, actually they count the words I, me, my, myself. They can't use those words because those words carry some psychological or cognitive meaning instead of just ignore it. But the computer side is just ignore it. So it totally depends on you, like I said, depending on your research objective, you need to retain them or you need to ignore them. So for this sentence, I remove all the stop words. Let's see what's the first term words are: earnings, inequality, effect, social, security, finance, etc. Right? I still need to remove all the punctuations. And this stuff, right? I still from string import punctuation, and then the same thing, right? From the word in this token clean, if word not in punctuation, let's see the first term words after removing punctuation. It's earnings, inequality, effect, social. Yeah. While you're seeing this, I suggest you just push, kind of enter and try to run on your end, because it seems to be very easy. It's not that easy if you want to run by yourself. Yeah. So try to follow, try to press enter on your end. But still something not good, like earnings. What do we really want to earn and earning? They are the same thing. Or earning, earnings, earnings. The three words, they are the same thing. But if we count them as different, count them differently, you will expect we will have a vector that we will have a space treat these words in a different way. For computer scientists, it's very interesting. For computer science, they don't care. They found a way, they ignore all those variations of these words, the same words. And that's okay for computer scientists. Like bird model, they actually ignore them. They just treat them as the same one. But for us, my experience is, it's very important to pre-process the text so that the noise can be minimized. Otherwise, your result is not that accurate.
So forgive me if you already said this, but the 10th word.
Yeah, the first
in output 16. Look at the 10th word.
This one?
Yeah, not a word. How did that happen?
It's just a typo. It's just a typo of its original word. Yeah. It's not either, it's just a typo. Probably it's from the typo in the original document, or it's a typo from the OCR process.
Yeah, it's in the. Let's see.
It's in the
If
source.
you scroll, you can see it.
Yeah, it's a typo, right?
Or scroll.
It should be a
Oh,
typo.
I'm sorry. Bottom.
Let me just see the
It's in the original document.
doc. It should be there. It should be in
Yeah,
the
the
original.
text of it is.
Yeah.
Well,
Lali issue, the issue,
validity.
lality. Yeah. Probably it's kind of a term, a name of an issue, something like that. Yeah. I'm confident to say that it should be from the original document, because we are not doing anything we are not revising the word itself yet. The word, we are just let word be itself.
So you could pre-process with like a grammar checker or spell checker.
Yeah, spell check.
Stuff like
And
that.
now it's more like removing the nonsense words to minimize the noise, to minimize. For us, for social science, and for us to do research, we need to be very careful about each state. If we introduce a lot of noise, the end outcome will be not meaningful. Yeah. So we need to be very careful at the very beginning, pre-process that. So here, there is a brutal way to process those variations of words called stemming, or called Porter stammer, which just remove the last few words of a sentence. So here we see the earning change to earn, EARN, inequality change to EQU. It's not even a word anymore, right? Stammer is try to expose the stem of a word instead of word itself, right? But it's in a very, it do this in a very brutal way because it just cut the rest of the world, word. Now let's see, let's compare. Okay, originally the document has tokens. When I say tokens, is almost equal to words, but it's not necessarily equal to words. Sometimes question mark is we call it tokens. Originally, it has 1,457 tokens. After we remove the stop words and remove the punctuations, we have about 1,300. After we do the stemming, we have about 1,200 tokens here in this text. So you want to expose the essential information contained in the text, remove redundancies, remove kind of noise. That's what we're doing here. Still, we see a lot of things a lot of ways we can improve this. Rachel, that question?
Stemming doesn't remove words, right? It's just counting the distinct number of the stems. In that.
Stemming does not remove a word. It's cut the word. It's cut the word. It remove the bot. It remove the end several characters of a word. Yeah.
So I was just saying that because the number increased when they counted the same number of the clean tokens, but
yeah,
it's just because it's counting the distinct.
Yeah, it's just this you mean you see the set? The set is used to count just put them a set. So in the set, if the two items write in the same way, they will combine same one. Like the earn, probably it will appear multiple times. Let's see that how many times it appeared. S for S, and if S equal to then okay, it appears for these times. How many times? 141 times. So for these 141, they will be counted as one. So if I just use set, which is 1, and make sense? Yeah, it's not a function of the stemming. It's the way I'm calculating. Yeah. Okay, let's move on.
I'm sorry, I bet others are having this issue though.
Sure.
I keep getting this message saying file changed, and do I want to update it? And I'm afraid to, because is there a source file on the server? Is this all happening here?
Yeah, you can just overwrite.
Oh, really? Okay.
Yeah, no problem.
This is only the local copy then.
It's just it's a kind of remote copy, and not my copy. So
Oh.
each of you will have a separate copy of your own.
Okay.
Yeah.
All right.
Not share. Yeah, not share.
They're all forked on this.
It's yours. It's yours. Yours.
This is stemming removing.
Yeah.
Prefix and suffix. It's just to remove the suffix. If you that's suffix. It remove the suffix of the word, not the prefix.
Yeah, I mean, how does this model work?
It has a list. It has a dictionary. It has a dictionary. It compares with a dictionary. It's not very advanced. Now we will see something advanced. Stanza is a neural network. Okay, we want to see how parallel machine is working. Let's open this. Edge top. So open one of the, you know how to open that, right? Click this. We do this again. Click this plus button, and then go to there's other terminal here. Edge top. Now you see you have here and drag it. You can just drag it here. Okay, it is not in the shape you want, right? Control C, terminate it again, and rerun the command again. Okay, it will adjust the shape to fit your window size.
What's the command?
Yeah, wait.
To fit the window size.
Just to rerun it.
Okay.
Control C is terminate the original command. Or you press F10, it will exit as well. Control C is a brutal way just to terminate currently. Yeah. F10, F10 is not working. It should work. If it's not working, just Control C. If you're a Mac computer, probably there should be some Command C somewhere there. Yeah. Are you there? Jason, are you getting it? You cannot stop it again?
Yeah, yeah.
You got it? Okay. Stanza. This is tokenize and remove stop words according to universal part of speech tags using Stanza, English only. It can deal with multiple language. Here we just use English. What is a universal POS tags out of speech tagging? I provide you the URL. So here, this is a universal POS tag. Open class words, closed class words, and others. ADJ, INTJ, pronoun, verb, a lot of words here. So here, what I'm doing here is I'm removing the words according to their POS tags, according to the function of the words in the sentence. Make sense? So I will see verb is very important information I want to retain, right? And also noun is very important I want to retain. So I'm retaining these words according to their function in the sentence instead of just the remove them according to a list. Make sense? So here, what I'm removing is DET, SYM. What are those? DET is determiner, okay, and SYM symbol, which will, if you click them, it will include something like this. But if you are doing, say, Twitter, if you are analyzing Twitter message, you definitely don't want to remove this, right? But these symbols are very important in Twitter language, right? Twitter text. So it depends. Again, it depends on your user scenario. And here you can see SYM in other language. CS, show you other language. DH. Most of them is here, so it doesn't matter which kind of language you're using. The function of these words, of this token in your sentence is the same. I remove a lot of stuff. I don't think they're important, like this conjunction, S conjunction, ADP, X, AUX. You can click into each of these words and see what they are. As conjunction, subordinate conjunction, give you some example. Believe that, if, while, something like that. Yeah. This is a more advanced way, a nuanced way to remove this. So when I do this is, okay, Stanza, I establish a pipeline, language I specify to English. Process, I need a few process, tokenizer, multi-word tokenized, which means some words can be tokenized together. Like University of Texas also, probably they will be the same. They are not tokenized all those words according to space. POS, part of speech tagging, tells you which kind of, what type of language of this. What's the function of this word in your sentence. And the lemma is lemmatization. What lemmatization is? It is an advanced way of stemming. Stemming just exposes the stem, right? But lemmatization exposes the meaning. Lemmatization usually refers to doing things probably with the use of vocabulary and a morphological analysis of words. Normally aiming to remove inflectional endings only and to retain basis fictional form of the word. Like here's an example. Look at that. Like this example, change stemming or change, all change. Lemmatization. What's the difference? Yeah, you see the E. Stemming, just to remove all things after E, with E together, right? Just to remove. So this is a channel. It's kind of a
the base.
last name, yeah, just directly cut them. It's kind of last name. Sometimes you can probably mess it with a last name of Asian origin people, right?
So the lemmatization is recognizing that it is the word change, the meaning change. Or the stemming is just recognizing the like CHAN.
Yeah. It's just to remove all things after CHANG. But lemmatization is more nuanced. Like a change, changing, changes, changer, change. It exposes the meaning words or morphological words I think they call it in this way. I can be wrong. I'm not a linguistics, so. Let's execute this. It will download a few items. It tells you the process now you are using CPU. We load all these pipelines. Each of these pipeline is a linguistic model, is a kind of a neural network model.
So are those layers inside one neural net or are those multiple neural nets?
Multiple. They are different. They're separate from each other. You are building a pipeline. So you are putting different model, different neural network models, layer by layer, right? Like a pipeline. That's why it is called pipeline, right? Yeah.
What's the data type at this point? What is outdoc?
Outdoc. We are not there yet.
Oh, I'm sorry. I
Yeah.
thought, oh, okay.
So what we have now is only doc. So you see the NLPEN is what we have here, right? We are setting the NLPEN as this function, not function, but a class. Right? What we need to do here is feed this NLPEN with the doc. The doc we have. The doc we have is this, right? Just a random read doc. Now we feed this with. Now we will have our outdoc later. It is running. If you go to this page, so the machine is running. This guarantee they're running just since it's just one document, and we are using CPU. It's so slow. I will tell you, this is from one of my this text from one of my research projects right now. I'm actually using GPU. CPU is too slow. GPU will be 100 times. I would say 100 times faster than CPU, but we just have one doc here. So you see the doc. Now we will have a doc here. Let's see where. Now we have outdoc. Let's see what outdoc looks like. Not show them all. You should first check document. Yeah. Another way to know what are there is you see you put the dot here, input the dot here, and press tab on your keyboard. Then you will see all the functions you have. It makes too much sense, right? So I want to know the content of it. I just use to dig because you cannot put the original stuff here. So I use to dig. It will be a long dictionary like this. ID 1, how. Text is how. Lemma is how. UPOS, I usually use UPOS. XPOS is what I don't remember exactly, but it's kind of a different label system. UPOS is universal part of speech tagging. It's an adverb in this sentence. The fits, I don't know what that, I don't use it very often. Start character is from the first word, the first starting. In Python, the starting character is 0, you know that, right? 0, starting with 0. To character 3. Does the lemma, look at this one. Does the lemma is do, right? Is an auxiliary word, AUX, etc. It lists all the words. Okay.
Is there a way to just get the first view?
Yeah. Let's say the first attempt. First time I like this. First attempt. This is a list. Essentially, this is a to dict. It will show you a list of items. And I asked the computer just to show you the first attempt. That is from 0 to 10.
So it translates the document data type into the dictionary.
Yeah, this is a Stanza stuff. This is a Stanza. You see, is a kind of there are different types of data type in Python. So this is you see. It seems like it's a kind of a list. No, it is not. It's an object. It's a Python object. TIPE type. You should be able to know this type. It's a kind of a Stanza document. It's not a list. So you need to use the toDict to transfer this kind of object to the common data type we have in computer, in Python. That's how we do it, right? You see this. We can keep doing this. We will see this later. Now I want to see the average sentences, average length of sentences. The average length of the sentences are 26 words, 26 words. Yeah. So you see the first, it spits out all these sentences. The first sentence has these words, has 9 words. Do you see that? It helps you cut the sentences as well, because we have a function here specified, tokenize no sentence split. This has been sentence split equal to false. If we set it to true, it will not spit out sentences. It will just spit out, it will just output one long sentence with everything. But now let's just set it as false. Okay, what do we need to do is, okay, now we have the,
I'm sorry, how does it know what the sentences are if you remove the punctuation?
it's punctuation not removed right here.
Didn't that happen earlier?
Yeah, we did that in the NLTK, we directly remove them. But here, what we are doing, what am I doing right now? We are tagging them. Instead of pre-processing those texts, we actually are tagging them.
You're going back to the original document when you do this processing. You're not using the process text that you generated in previous. Right.
What do you mean? So right now,
There are various steps where you remove punctuation and a couple other things, but
Yeah.
I think you're going back to the version of the data from before those steps and putting that into Stanza.
no, it's a separate, sorry, I need to clarify that. Yeah, it's a different, now we are starting everything from scratch. So right now with NLTK, I'm introducing you a very brutal and native way to do the text appropriate preprocessing. Now with Stanza, I'm introducing you a more advanced way or nuanced way to do text preprocessing. What we are doing right now, we are not doing any preprocessing with the text yet. We are just tagging them. We are just tagging them. See, all these words, they have a tag. They have a lot of tagged information about these words. Do you see that? Lemma, earnings, lemma is earning, right? Yeah. Inequality like this. Number string equal to string.
So will we always want to grab like the value assigned to the lemma?
It depends. It depends. Sometimes you probably want to use Porter statement as well. So it really depends. And it also depends on the results. In my research, since most of my research deal with the semantic meaning of all these words, I use lemma all the time. Most of the time, I should say, most of the time. But for some of the tasks, like what dot to back or word to back, if I have to try to treat the words as strings, I think a Porter statement probably is a better job than the lemma, because you see lemma sometimes they treat earning and earn. They are two different lemmas, right? In a system. But if you stem them, they are same word. They are the same word. That makes sense. Yeah. It really depends on your research, and we need to think them through and need to justify them.
So that's like one of the questions you need to ask, like in the research design.
Yes. Yes.
So then
Yes.
the stemming versus the.
Yes. It's all those caveats. It's very important. Not every reviewer will pick it up, but we are very clear about this. Another reason I'm not using I'm not saying anything about R is bad or something, right? The reason I found R, why I'm using R do the natural language processing and network analysis is not satisfactory is because they have a lot of stuff preset. You are not really very clear about what is going on behind, right? They say they pre-process text and then spit out the text. Then I need to know whether they there are stemmers or lemmas or whatever, right? I need to be very clear about this. So usually what I do is I will read the source document. So in the source document, you will see there are a lot of parameters. I will read through all those parameters instead of just accept the default. Let's take a quick example here. So like this, these three, there are three parameters here. Count, index, left, or right. In my research, I need to be very clear about what are each of these parameters, what's the meaning of each of these parameters. Instead of just, okay, let them set as default, like this one. It has a lot of it set as default. Max sentence length is about 10,000 and the limit bottom now. So I need to be very clear about why it is so. Right? That makes sense. They have explanation. All this documentation has a very good explanation. Let's go back to the doc here. Okay, try a sentence. Word lemma. I just need the word lemma for word in out sentences. The 33rd sentence. If a word POS not in remove list. If it is in remove list, I would need to remove them, right? So I only want to keep those words that has a POS tag not in my remove list. What I have is here. Taxable, maximum, adjust, change, consumer price, index, urban. What the original sentence looks like. Let's take a look. Original sentence, the taxable maximum is adjusted by the change in the consumer price index for urban, wage, earners, etc. Now what we have here is taxable maximum adjust, change, consumer price index, urban, wage, earner. Clerical, okay, worker, those words like this. Yeah. You see, they're pretty clean. No S, no ing. Ing probably they will retain the ing version, but they're pretty clean here text. Then I want to iterate all sentences. This is just iterate all sentences. I put them together. Okay, let's see. We have after using Stanza, we have 1213 clean tokens. What do we have through the other method? Tell, yes, tell. It's not dramatically different. It's not dramatically, but this is just one example. So pre-processed text, I will skip this. What we did is we did document by document. It's very slow. If you have 10,000 or 40,000 articles, do this one by one will consume probably forever. So you want to batch process. First, you want to batch process. Second, you want to multi-process. There are different things. But I have the code here. You take a look. Essentially, for this code is just a process 5, say 10 or 5 documents at the same time, instead of process 1 document at the same time. I'll skip this. Let's do the next. NER with Stanza. We want to do the name entity recognition. We want to recognize the institutions or entities within the text. What we can have here is, again, NLP equal to Stanza pipeline. I establish a pipeline. I specify language as English. Process is tokenizer. For this pipeline, for this task to work, I need to establish a pipeline that is with 2 models. First, tokenizer, then NER model, NER language model. It's just execute this. Now we have here, doc here. Docs 2. Docs are all the doc. We can do the doc here, and then do docs. we use the same document as we used in the previous section. Okay. So it is running, it take a little bit of time, but you are confident. Let's see that. Okay, we are confident. It's using most of its code. Okay. Let's print out all the entities recognized. Okay, it recognized the Urban Institute as an organization, 5% as a percentage, year as a date, Social Security as an organization, Washington as a global kind of problem position, brief paper organization, briefing paper. It can get wrong. You can get wrong. Feeling, money. You recognize this as money. Person. 28% as a percent, etc. Now we want to know all the organizations recognized. I just select a random sample of 20 examples, not all of them, just the 20. Social Security, Social Security. It's almost a typo, but it's a good job. AARP is an organization. Smith, 2018, should be a paper. Congressional Budget Office. Yes, this is a organization. Fiscal Responsibility, Social Security, Urban Institute, National Commission. Yeah, you see the results are very messy. It's not exactly as great as you expect. So the accuracy, I think the original accuracy is only about 80%. They have a benchmark. Another trick is when you next time do this, you want to know the benchmark as well. So they have a lot of performance. So you want to pick up the best kind of model and then produce a result. Also, you want to validate them. You want to validate the result according to the research. Or just use these results, these kind of machine produced results as first state. You have to, it's not definitely not ideal, but it's just the first state. There are many flexible we can do that. Like if I have an organization list, if I have a list of organizations, I can use that kind of a dictionary. There must be a kind of a supervised approach, right? Because I already know these organizations are my target organizations. So this will greatly improve your accuracy of your study. So far, what we're doing now is preprocessing. What do we cover? Removing stop words, removing punctuation, just in one sentence, we want to retain the meaningful words instead of non-meaningful words. There are many different ways to do that. Use NLTK, where I use dictionary, where I use a very native, but a simple method. It's fast, it's very fast. We can also use POS, use a more nuanced way, refine those words or retain these words according to their function in these sentences, instead of just delete them or retain them or use statement or something like that, right? So these are stanza can help us, but it takes extremely long time. So GPU is very necessary. We want to do that. The package you are using, the image is GPU capable, but you still need to spend a lot of time to setting up your GPU environment. Are you using GPU or not? This will tells you. Use device GPU, CPU, when I use it. And also you need to specify here, use GPU, in the pipeline, you need to specify use GPU. True. We are going I tell you, we are going very, very fast. So for this document, go home, when you go home, read through each line of this. Make sure you are very clear about each line and each parameter about this. It takes a lot of effort, a lot of time. Okay, what document? What to back example? Let's do a what to back example. Okay. See if you can run this block directly. If you can run it directly, that's okay. Don't run this block. This block will take a lot of time. Don't run this block again. Directly run this. I already run this, so I'm here. What is what to back? What to back is very much like a kind of a word dictionary. What is a dictionary? For each word in this dictionary, it gives you They give you a vector. Like this computer. It will give you a vector like etc. And the dimension, I guess, probably is 552, 512. Let's see. $300. Okay, 300. Oh yeah. We are using the Google News 300. This 300 is the dimension. It has 300 dimension, this vector. For each of the word, we can expect each word. It will be a dictionary like this. So you can use it as a kind of a lookup dictionary. Then you will be able to find the vector value of all words. Apple. Sometimes it contains typo. No, not this one. APPL. APPL. Probably this is Google's stock ticket. The symbol is stock ticket. That's why we have it. The problem with what the WEC issue is, if there is a word is a typo or a word, the dictionary does not have the word, it will cause error like this one. It will give you an error saying key Cameron not present, something like that. Okay, now we have the vectors of the word, right? What we can do? We can do a lot of stuff with this. We can calculate their similarity. So I have a list of words pair here: car, minivan, car, bicycle, car, airplane, car, cereal, car, communism. So you see that the similarity is 69, 54, and the car and communism is 0.06. Right? So through this way we can calculate the similarity. I think this similarity is cosine similarity. They are calculating the cosine similarity. If you want to know what kind of similarity they are calculating, find the source code and read the documentation of the source code. Also, we can do another something interesting is most similar words with king will be kings, queen, monarch, crown price, prince, sultan, ruler, etc. The most similar word with chess. Yeah, do the chess. Research is grandmaster. Kasparov. Yeah, grandmaster. Yeah. Chief. Cheddar cheese, goat cheese, or something like that. So it's very basic, but it's it's very much like a 1 + 1 = 2. With this very basic fundamental tool, you can actually do a lot of very fancy analysis. So right.
This is a word to back based off of Google News.
Yeah. Where the model we are using is Google News. Now we are switching to a different model, which is larger, which is much larger. So I think you already run this already, right? So you have the model here below. This is a web page. You can take a look. Global vectors of word representation. They have a lot of training data here. They have a lot of kind of models here, like this one. Think of these models as dictionary, where you can just look up those vector words, so you don't have to train for yourself, right? Actually, it tells you what kind of words they are using, and these model have 6 billion tokens. They also have Twitter. 2 billion tweets. Something like that. Yeah. 25 dimension, 50 dimension, 100 dimension. Usually, if you have higher dimension, your calculation, it actually give you a finer kind of distinction between two different words. Because you know the dimension, when there's more dimension, there are more information retained by that dimension, right? But it also exposes a computational kind of challenge, because it's very hard to calculate 200 dimension by 200 dimension when you have 1,000 or 10,000 papers. So sometimes I use 200, 300, or sometimes 100. I think that's good enough. It's good enough. So these commands are shell commands. They are shell commands. It's just more convenient to run this shell command. I start with exclamation mask here, make dir, make a directory globe called globe, and then I enter into that globe directory, and then wget is I download this globe.6billion.zip, and I unzip this file. It's very straightforward. The total file is about 800 megabytes. Another reason why I need to use this server is because server is fast, not only for computation, but also the network is fast. So for this, I have about 4.995 MB per second. Now I have all those docs there. For this, you can read by yourself, but essentially this chunk of code just set the read the document, and then tells you make them a model, and then the model will be the same like the WV we just saw. We can see the happy. We can see the happy. This is we are using the 50 dimension. The happy 50 dimension is like this. What's very interesting, you can compare. Now what you can do is you can compare the words, right? The same happy, will they have the same location in two different models, or they have the same model, right? So Google News, the previous model we are using, they trained through using Google News instead of other. But for this one, they are using Wikipedia or something. So if we can train model using different kind of corpus, then we can compare how kind of the semantic meaning of words are different in different corpus. These corpus can be political text, and it also can be folklore text. Then you can compare the same identity, how people, the most similar. You see the most similar? The most similar words around king in political text, and the most similar words around king in folklore. Most similar word, happy. I am happy. That. Everyone is happy. Everybody is happy. Really happy. Happy me, definitely happy. Maybe happy. Feel happy. I'm happy. And let's see what's similar word you're not happy. Okay. Most similar. Right. Glad. Thieves. Oh, look at that. All these words. They must be in the this is very much like a news, right? It's very different. Because these are more oral. These words are more oral. These words are more kind of written language. A lot of possibilities. You see, you must be able to see a lot of possibilities with this very simple operation for social science research. What we're covering right now is all about words. We are not covering sentences, or we are not covering the entire document yet. In research, you probably want to calculate the similarity between two documents. What we can do is with what mover distance. Give you a quick example about what mover distance is. So look at this example. There are two sentences here in the semantic space. Obama speaks at Illinois. This is one sentence. Second sentence is if the president greets the press in Chicago, right? You see that? So if we visualize the words in the same semantic space, we want the distance between Obama and president is very close, right? The distance between greets and speaks is very close in comparison to other words. There's another example here, which will give you a better example idea. So it calculates the distance. Like another sentence is a band gave concert in Japan. So the distance between Illinois and Chicago is 0.18, and the Japan between Chicago is 0.28, right? It's longer. So if you combine them, add them together, the sentence, if we move this sentence to this sentence in the semantic space, it will cost us 1.63. Very similar to the editing distance, but not exactly the same, but very similar. What we are now is not a string. We are in the semantic space. We're in the semantic space. For this sentence, we have kind of a closer distance, 1.07. Obama speaks media. That's what we call word mover distance. What we can do that is we can calculate that very easy. Let's use a word still the same model. Sentence Obama, sentence president, sentence else. Word mover distance is an established function, very quick. Sentence Obama, sentence president. Let's calculate the similarity. Oh, not fine. Sorry. No model name. Look at that. Need to install. Okay, now we have a similarity. The Obama sentence and president sentence, the similarity is 4.4, and Obama sentence and else sentence is 4.6. Here it is not similarity; it's the distance. Make sense? The distance is smaller, so the similarity is higher, right? Do you get it? So if the distance is smaller, so it's calculated distance like a cost, right? If the distance is smaller, it means that the similarity is higher. It's a reverse. It's a reverse. There's a reverse of the similarity. The president and else is 6.2. The distance is higher. Yeah. What do we do now? We are using a single language model. What we can do is we can use a multilingual language model here. This is a universal sentence encoder multilingual. I think it supports about 16 languages. Let's take a look. It has a lot of versions. We are using version 3. I think they support 16 languages. All these languages are supported by this simple one model. So we load, embed, load this model from this URL. Okay, now we have doc1. 高兴 Chinese means happy. Pets is lovely. 狗狗真可爱 Pets lovely. 出去走走 go out. Take a walk. And this sentence is pets are our good friends. Happy learning. This is doc1. We need to encode this doc. So this embed this doc1 and output it as a numpy as a vector. So let's see what we have. We have 1, 2, 3, 4, 5. We have 5 documents here. I just use a very short sentence to indicate there are 5 documents here, right? But you can have longer, say 15,000 or 1,000 documents. But there are some caveats. Look at there are some caveats about the length of document. On the web page, I have a section about that. Max length of input documents, caveat 1, caveat 2. This is very important because sometimes if your document is longer than 500 words, the rest of the document will be cut. You don't want that to happen, right? You don't want to happen. So we have a second document 2. We have 2 sentences. This means pets are our good friend. Happy learning. It's just a literally translation of this happy learning here. This is document 2. We have 2 documents here, 2 vectors here. Now we want to find the inner product of the 2 vectors. Then we will see the similarity. So these are the similarity. These are the similarity. And you should do that. This, okay, have it.
So this is looking at 2 different documents in 2 different languages.
2 different languages, multiple different topics. All the docs are different. They are not the same docs. So this is the similarity matrix we have. So this is the doc 1 here. Or we can say we use A1, A2, A3, A4, A5. And here will be B, B1, B2, right? So B2 is happy learning. This is happy learning. Happy learning. And happy learning is here, right? So we can expect this should have a very high number here. It's about 76. You see here? 76. So this is also very high. A4 and B1. What's A4? A4 is 1, 2, 3, 4. Pets are our good friends. And B1 is 动物是我们的好朋友, which is literally the Chinese translation of English. So we have a very high number here. Make sense? So you see, the strings are not important anymore, right? You see the translations, although they are in different strings, they are in different languages. We can calculate them. Once we have the vectors, once we have these vectors, it's not a kind of it's not a strange language to you anymore. They are numbers, they are meanings which you can calculate. So this is an inner product to find the cosine similarity. You can also use another way to calculate the cosine similarity. The spatial distance between 2 vectors is cosine and then minus by 1. This is another way we can calculate the inner product of the 2 vector series of vectors. The results and visualization should be the same. Just the 2 mathematical ways to calculate vectors. Surprisingly, we finished on time.